Today's lecture is on antiderivatives. So up until this point, we've been obsessed with finding derivatives of things. But of course, everything that we can go in one direction, math always has an undo button, right? So if we add a number to something, we can get back to the original number by subtracting. If we multiply by some number, we can get back to the original number by dividing. And so we need a way to go backwards. If we have the derivative, then what do we do? How do we find y? Right? So this is y prime equals 2x. So I don't think it's a terrible stretch of the imagination to kind of guess that y has to be x squared, right? Because then if we did y prime, we would immediately get 2x. Now, you might notice that actually this could be the derivative of a whole bunch of different functions. What if I had y equals x squared plus 2? Or y equals x squared plus 6, or y equals x squared minus 4. In all of these cases, I would end up with a derivative that is 2x because the derivative of the constants, they just turn to 0 and they drop off. So for that reason, right, we say that y is actually is x squared plus some constant that maybe we lost when we did the derivative. So the way that we write this then is that we say that the antiderivative of 2x, and we say dx after it, that's like saying that my variable here is x and is equal to x squared plus c, okay? So this x squared plus c is my antiderivative. So if we kind of think about the same thing here, then if I have y prime equals 3x squared, it's not terribly difficult to think, oh, well, what could y be? Well, y could be x cubed, right? Because if I do the derivative of that, then I multiply down the 3 and then I get x squared. But again, my y could also be x cubed plus 4, or y could be x cubed minus 100, whatever, right? So we say that the antiderivative of 3x squared, this is like with respect to x, for the dx, is equal to x cubed plus c. This is a general antiderivative. So basically, it finds a whole family of antiderivatives that are equal to the derivative because of the plus c, because when we do the derivative, we lose any constants, so to make up for that, when we go backwards, we tack on a c. So let's just look at some graphs real quick. I just wanted to show you, so my f of x is x squared, right? So I just did essentially, so these are like all the, I mean, I could keep going on and on and on, but the antiderivative of 2x is x squared technically plus c. And so I'm just graphing a whole bunch of possibilities, right? So unless I have some initial value, basically, I just know that it comes out with a family of functions. So this would be x squared minus 5. This one looks like x squared minus 3, minus 2. Here's a plus 1, plus 3, plus 5. And they could go on and on, whatever c is. It's like a whole family of functions. So the same thing, if I changed my x squared to my x cubed, right, then I have this whole other family of functions. Here my f prime would be 3x squared, but when I do this, essentially, I get this whole family of functions. It's not just one thing. It's like the general antiderivative, so it's any of these three, x cubes plus any constant. I just did, again, like negative minus 5, minus 3, minus 2, and plus 1, plus 3, and plus 5. But I could go on and on and on, like minus 100. Like essentially this plus c part here just means that it's going to give you a whole family of functions, okay? So this brings us to our definition of an indefinite integral. So it's noted that this is the integral of f of x dx is the antiderivative of f if f of x is if capital F of x is the antiderivative of f, then the integral of f of x equals cap f of x plus c. So in our example, we had the integral of x squared dx, oops, I should have put my dx in there, sorry, is equal to x squared plus c. So in this case, our cap f is the x squared plus c. The antiderivative is always the capital F, okay? So some properties of indefinite integrals before we start using them. We're going to let cap F and cap G be antiderivatives of f and g respectively. So that means sum and differences, like if I do the integral of f of x plus or minus g of x, then this is just, I can just add the antiderivative. So it's just like when we were doing the derivatives, we can do each antiderivative separately as well. And then we also tack on the plus c because we might have lost a constant here. And also if there is a constant multiplier, right, we can actually write it on the outside of our integral and then just multiply our antiderivative by it in the end, okay? So it's important to note that there is no multiplication or division rules for antiderivatives. So we're going to go back to very, very simple kind of things, okay? So we're going to kind of go through the derivatives we know and then figure out what the antiderivative will be, okay? So we know that to do a derivative, we multiply down the power and then we subtract 1 from the power. So to go backwards, right, so first we multiply, right, and then we subtract, right? So that's this order, right? That's that way. So if we're going to go back from subtraction, we're going to add 1 to the power, so it'll be x to the n plus 1, right? So we're going to go this way, we're adding. So we subtracted 1, so this time we're going to add 1, and then we multiplied by the power, so we're going to divide by the power. So that's n plus 1, okay? And this works for all n not equal to -1 because when I plug in -1, I divide by 0. So just, right, so just to quickly go through, right, if we had the like x squared, and I want to do the antiderivative of it, this is x to the 1 more power is 3, and then I divide by the new power 3, and then plus c. Forgot my plus c up here, okay? So just an example of that. Okay, so now if we go through the rest of these, so we know that the derivative of sine is equal to cosine of x. So that means that the antiderivative, this is why it's so important to know these derivative rules, the antiderivative of cosine of x dx is equal to the sine of x plus c. So anything we know the derivative of it, we basically can find the antiderivative of its derivative, okay? So the derivative of cosine of x is negative sine of x. So that means that the antiderivative of negative, actually I'll put positive sine of x here, dx, is equal to then, these have opposite signs, so this is negative cosine of x plus c. Right, so we know that the derivative of tangent is secant squared x, which indicates to me that the antiderivative of secant squared x is equal to tangent of x plus c. Got to know those rules for our trig functions. So the derivative of secant is secant x tangent x. So that means that the antiderivative of secant x tangent x is equal to secant of x plus our constant. All right, so we can go through the rest of these really quickly. So the derivative of cosine is negative cosecant of x cotangent of x. So that means that when I do the antiderivative of cosecant of x cotangent of x, this is where my signs are opposite again. Oops, I keep forgetting my dx. This would be negative cosecant of x plus c. Right? Cotangent is negative cosecant squared x. So that means my antiderivative of negative cosecant squared x dx is equal to, actually let me make that positive, so then it'll be negative cotangent of x plus c. So they're opposite signs. Now, e to the x is the greatest, right? Because that means the derivative of e to the x is e to the x, so that means that the antiderivative of e to the x dx is also e to the x plus c. All right? So a few more here that we do know. So some other derivatives that we knew. Now, we're just going back to basic derivatives here. So the natural log, the derivative of it, is 1 over x. So that means that the integral of 1 over x dx is equal to the natural log, and we say the absolute value of x plus c. So this takes care of our x to the -1 case. This is when our power rule fails, right? Because this would be x to the negative 1. So if I was doing x to the negative 1 and tried to use the power rule on it, I would add 1 to the power would be x to the 0 over 0, which then, so that when the power rule fails, it's the natural log. And we put the absolute value of x in here because the natural log has a domain restriction on it. So the derivative of arctan is 1 over 1 plus x squared. So that means that the antiderivative of 1 over 1 plus x squared dx is arctangent of x plus c. So it's a good thing to really put these in your memory so you recognize them, right? So the derivative of arc sine is 1 over the square root of 1 minus x squared. So that means that when I come across 1 over the square root of 1 minus x squared dx, this is arc sine of x plus c. Arc cosine is negative 1 over the square root of 1 minus x squared. So that means that the antiderivative of negative 1 over 1 minus x squared, or I could say positive, then this is negative arc cos of x plus c. Okay? So those are all the basic ones we know the derivative of. Now you might have noticed that back here on the other page, when we were looking at the derivative of the trig functions here, right, that we don't have antiderivatives for things like tangent or plane secant or things like that. Those are things that we will develop with some more time, but these are the basic ones. These are the ones we can start out with. Okay, so let's just do some basic antiderivatives here. Okay, so you kind of have to do a little bit of thinking backwards here. So the antiderivative of sine is cosine, and since the derivative, so when I'm doing these, right, when I do all the derivatives of things that start with a c, I always end up with a negative derivative. Now in this case, actually, whenever I write the antiderivative of something c, it's also negative, right? So here, this is actually negative cosine of x, because when I do the derivative of negative cosine, I'll get positive sine. So then the antiderivative of e to the x is e to the x. That's the best one of all. And then I have x to the fourth, so I need my power rule here, which is I'm going to take x to the 4 plus 1 is 5, divide by 5, and add my c. And there's my antiderivative. Okay. So again, I have e to the x. That's the easiest one of all. The antiderivative of e to the x is e to the x. And then I notice secant tangent, and I know that secant's derivative is secant tangent. So that means that the antiderivative of secant tangent is secant of x. And then this 1 plus x squared plus 1 is the derivative of arctan. So that means that this is arctan of x. And then I tack on my plus c, of course. All right, so one more. We just have a polynomial here. So it's all power rule in this case. So my antiderivative is 3x. I add 1 to the 2. I get 3 over the power. I always add 1 and divide by the new power. I have minus 4x. Now I'm going to add 1 to the 1, which is 2 over 2. And then my plus 6. Okay, so this one doesn't have an x, but remember that when we do the derivative of something linear like 6x, the derivative ends up being 6. So when I have a constant, I tack on the x, and then of course I have to account for another plus c. So this one I can simplify a little bit and say that my antiderivative is x cubed, minus 2x squared plus 6x plus c. Okay, so what if we want to find f, but we're given f double prime, okay? So remember that the antiderivative is the inverse, essentially, of the derivative. So that means if I want to find f, then I'm going to have to go backwards. Remember, it's f of x, right? Then we do the derivative and we get f prime of x, and then we get f double prime of x. So I'm going to need to go backwards twice, okay? So that means that f prime of x would be equal to the antiderivative of f double prime of x, which is 6x squared plus 12x, that's just a 6x there, plus 12x squared dx. And so this is going to give me So this is a plain 6x here, so this will be 6x squared over 2. This will be 12x cubed over 3 plus c. So to simplify this a little bit, my f prime of x is now equal to 3x squared plus 4x cubed plus c. All right, so I still need f, so I'm going to need to go back one more step, right? So I did the antiderivative and got to here. Now I'm going to do one more time and get to here. Now we don't know what c is, so we're just going to leave it there. So that means that f of x will be equal then to the antiderivative of f prime. Right, so we do our power rules all over again. So we're going to have 3x cubed over 3 plus 4x to the fourth over 4 plus, then this is a constant, just like the one in the previous example. It was a 6, but this time it's just c, so it becomes cx, and then plus, I'll put d here on the end as my constant, because I don't want to imply that it's the same here, so I'm just going to choose another letter. Okay, so my f of x is, simplifying, x cubed plus x to the fourth plus cx plus d. And that's all that I can tell you from right now. Okay? Now, there's future examples here that we'll be able to find the c and d if we're given more information. But right now, that's all we have. So let's find f. If we have f double prime is cosine. So my f prime of x will be the integral of cosine of x dx, the antiderivative, right? So this will be sine of x plus c. Remember, the derivative of sine is plain cosine, so there's no minus. I know it's easy to mess these up. So then that means that my f of x will be the antiderivative of sine of x plus c dx. So now I'm going to get negative cosine of x, right? Because the derivative of cosine is negative, so the signs are opposite. And then plus cx plus another constant d. And that's all I can do until I'm given more information. Like here, for instance. So now we have f double prime, but we know something about f and f prime of x. So this time we can narrow down. So for the previous ones, we got whole families of functions. We looked at the graph. Now this one, we're going to pick a specific one. Okay, we're going to actually figure out which one specifically it is, given this information. So to go to f, I know I have f double prime, so first I'm going to go to f prime. So I know that f prime of x is equal to the antiderivative of 24x squared plus 2x plus 10 dx. So this is going to give me here, I'm going to end up with 24x cubed over 3 plus 2x squared over 2 plus, my constant always gets tacked on an x, and then plus a c. Here's my f prime for right now. So simplifying it a little bit before I do anything else, I get 8x cubed plus x squared plus 10x plus c. Now I can actually get rid of my c here because I know something about f prime. I know that f prime of 1 is equal to negative 3. So I should be able to figure out what c is by plugging in this point 1, negative 3 into my derivative. So that means this will be negative 3 when I plug in x is 1. So that will give me 8 times 1 cubed, which is 1, plus 10 times 1 plus c. So over here I get negative 3. Here I'm going to get 8 plus 1 is 9 plus 10 is 19 equals c. And I'm going to subtract 19 over here, and I'm going to get c equals negative 21. All right, so now I can change my f prime. So my f prime now is actually now 8x cubed plus x squared plus 10x minus 21. Okay, so now I know that f of x will be the antiderivative of 8x cubed plus x squared plus 10x minus 21 dx. This will be equal to 8x to the fourth over 4. Let me move up here a little bit. Plus x cubed over 3 plus 10x squared over 2 minus 21x plus c. So simplifying here a little bit, I get x, actually 2x to the fourth plus 1/3 x cubed plus 5x squared minus 21x plus c. Whew. Okay, so let's see. I also know that f of something, f of 1 is equal to 5. So now we're going to use this one. So we know that the point 1,5 is on my graph of f. So now I can simplify this by plugging in. So I'm going to use the point 1,5 here. So that means 5 is equal to 2 times 1 to the fourth, so that's 2, plus 1/3, plus 5 minus 21 plus c. Ew. Okay, so I know my 5s are going to cancel here, and then I'm going to get, let's see, negative 19 plus 1/3, and over here is equal, plus c is equal to 0, so that'll be 19 minus 1/3 equals my c when I moved both of these over here. So for this moment, I'm not going to combine these. I'm just going to say my f of x then is equal to 2x to the fourth plus 1/3 x cubed plus 5x squared minus 21x, and then I'm going to say plus 19 minus 1/3. I really should combine those, but I'm just really not going to right now. Okay, so we can always, right, go backwards. So the antiderivative is essentially undoing the derivative, right? So if you have f double prime and you do the antiderivative, you end up with f prime. If you do the antiderivative of f prime, then you end up with f. So if you'd have the velocity, right, then to get the position, you would go and do the antiderivative of the velocity function. And that is our antiderivatives.